Okay, so 4 fundamental forces. All right, and these fundamental forces are the 4 that describe how matter interacts with itself. All right, so there are 4 of them. Does anyone happen to know what any of these forces are? Any guesses? Gravity. Oh, gravity's a good one. We all know that one. We experience that one literally every day of our lives. Does anyone know any others? What's the force that brings, well, what's the force relevant to chemistry? What binds electrons and protons? Yeah, well, we call it the electromagnetic force, right? The electrical force. All right, that's the electron, plus and minus charges, magnets, you know it, right? Does anyone know the other 2? They have polar opposite names to each other. Yeah, strong and weak. They're called the strong and weak forces. And those are very useful names, as we'll find out, because they're very descriptive. They're simultaneously not descriptive at all, but they're also descriptive. So what's called the strong nuclear force and the weak nuclear force. Okay. We'll talk a little bit about each one of them, especially the strong and the weak, because you probably don't know those particularly well. But what we should ask ourselves is, what are the relative strengths of these forces? Okay, so imagine you have 2 particles that, let's say you have a set of particles that interact just as the weak, just as the strong, just the electromagnetic, or just gravitationally. You set them all at the same distance from each other. How strong is the forces relative to each other? Right? What's the relative strength of the attraction or the repulsion? I'm going to erase this forces here so I can have a little more space. And the thing that what physicists call the strength of the force is the size of a constant. There's a constant associated with each force called a coupling constant, which sets the strength of the force. All right, it's just a number. It doesn't have a unit. It's just a relative strength, a coupling constant. All right, and we'll talk about what the relative size of these coupling constants are. And a nice way to think about it is let's just do them relative to each other. Okay, so let's think of the strongest force here of having strength 1. Right, and of course the strong force by its name is the strongest force. So the strong coupling constant is about 1. All right, so that's just like a normalized. Right, so now I want to compare everything relative to the strong force. The weak force is about 1,000,000 times weaker. It's about 10 to the minus 6. The electromagnetic force, interestingly, is exactly, compared to the strong force, 1 over 137. We'll see that number again later. That number there's a very specific, well-known number called what's called the electric coupling constant. It's 1 over 137. But that's the strength of it. And gravity, relative to the weak force, or a strong force, is 10 to the minus 39. Okay? So basically anything that interacts in the electromagnetic range, or the strong range, has no gravitational attraction. Right? Gravity, not surprisingly, gravity really only attracts very, very large macroscopic objects together, right? Planets and galaxies and universes and things like that. All right, so gravity, we can, for microscopic physics or like chemistry, we can just completely ignore gravity. And gravity has no communication at all. It's completely uncoupled, as far as we can tell, from the other energies or the other forces, and particles don't interact gravitationally. All right, so we have effectively, at microscopic scale, 3 forces: electromagnetism, strong, and weak. All right, so these are strengths, but the force has to be carried by something. Right? You have to have an object that carries the force from one position to another. Right? Think about the electromagnetic force. You have an electron and a proton. Okay? how is that force, and they're at distance from each other, okay? So you have an electron here and a proton here, and they're at distance to each other. They're not colliding with each other, they're separated, but there is some attraction to them. And the question is what is the object that carries that attraction, exchanges energy between the two objects, right? There has to be something that's effectively carrying the force between them, right? It's not like there's nothing between them, right? If you think about a proton and electron in a vacuum, how is that force between the electron and the proton how are they ever going to touch each other, right? There has to be some sort of medium or some sort of force carrier to transfer that energy from one particle to another. Okay. So each one of these forces have a specific fundamental particle that we call a force carrier, which is something that's exchanged between two objects that induces the force. Okay. So it's like it's actually what's called a virtual particle. It doesn't really exist per se. It's hard to explain what this means. It's like a formulation, kind of a way, an abstractification for us to imagine what's actually happening between, say, a proton and electron. Right? That this is this imaginary or virtual particle that gets created from one, collides with the other, and gets destroyed. Right? And that's what transfers the energy from the force. Right? So there's some physical object that transmits this force between two particles interacting with these forces, and they can all be found except for gravity. There's a lot of reasons why we can't find a force carrier for gravity. As far as we can tell, the only thing that carries gravitational force, right, Einstein tells us, is from the curving of space-time, right? That's what gravity is causing, from distortions in space, curving of space. And so gravity is effectively like you're causing space to, as you put a mass in it, space to bend and things roll into that hole that you fill from the mass. Right? You can kind of think of space as like a mattress, and your planets are bowling balls, and you stick the bowling balls on the mattress, and the mattress sinks around the bowling ball. Well, that's how space works as well. And so gravity comes from the fact that space is no longer flat. Now it's got a divot, so things can roll into that divot. All right, so gravity doesn't have a force carrier. Space, if you will, is that force carrier. So we'll ignore that one for now. Maybe you've heard in sci-fi books or whatever something called a graviton. This is a hypothesized particle that carries gravitational force from one object to another, but no one's ever observed that. As far as we know, it's just a physical effect of mass. So the other three have force carriers, and they're all very fundamental particles. The electromagnetic force, say the attraction force between an electron and a proton, is carried through a very, very important particle that we'll see constantly in this class. The force carrier electromagnetic field is a photon, light. Light is so you exchange light or photons between objects, and that's what causes the electromagnetic force to exist. Right? The light particle, the photon, transfer of light particle from one object to another is what transmits the electromagnetic force. Right? So electrons and magnets and all of that and photons are all intricately connected. Right? The photon is the fundamental object of the electromagnetic force. Right? That's why we see so many. And that's why light waves are intricately connected to electromagnetic particles like electrons and photons. Right? There's this interconnection between electromagnetic charge and light. Right? And it's fundamental, absolutely fundamental. So again, you understand what the electromagnetic force is, right? Positive, negative charges. The strong force is a very, very interesting force. The strong force is what keeps nuclei together. Right? There's two forces that keep nuclei together. There's the electromagnetic force. Well, let's think about it this way. Let me stop for a second. So let's think about helium. Helium has two protons. Let me find a pen. We'll just write it on the board real quick. So let's consider helium for a second. Right, we're going to find a problem with the electromagnetic force because, as you know, opposites attract. Right, so let's look at the helium-4 atom. This has 2 electrons, 2 protons, and 2 neutrons. All right, we'll talk about protons and neutrons in a second, but you know. But as you know, the way that this atom looks like is you have this inner core that's very, very small and compact that has 2 protons and 2 neutrons, and around it you have 2 electrons orbiting. Right? They don't really orbit like this. We'll talk about how electrons move around nuclei plenty in this class. But how do the protons and the neutrons stay together? Because first of all, 2 protons should repel each other, right? Because they're both positively charged. And neutrons don't have charge at all, so they shouldn't be attracted through the electromagnetic force at all. Right? So there has to be some other force that keeps the nuclei together. Right? There has to be some sticky force that's stronger than the electromagnetic force to keep them together. Right? It has to be stronger because it's really easy to pluck an electron off, but it's really hard to break a nuclei apart. Right? Very, very hard to break a nuclei apart. Right? You need to have very, very high. You need to have a sun to do that, right? Or you need to have fission. Right? You need to have a very, very high source of energy, a nuclear reactor. You need something like that to break this apart. Right? Whereas an electron, if you shine a light strong enough at this high enough energy, or you apply a voltage to it, you can kick an electron off. Right? So the attraction between an electron and the nuclei is quite a bit weaker than the attraction of all the particles in a nuclei. So whatever force sticks all the protons and neutrons together must be quite strong, and that's the strong force. And the strong force, the carriers, were not discovered until the 60s or something like that. And the force is the carrier of the force, the particle is called a gluon, right? Named after glue. Right? It glues the nuclei together. And it turns out it not only glues the protons and the neutrons together, but as we'll see in a second, protons and neutrons aren't fundamental particles. They're composite. There's an inner structure of protons and neutrons. And the gluons keep those together too. Okay, so the internal structure of the proton and the neutron itself. So we'll see they're composite particles. The strong force keeps those together as well. Right? So any sort of nuclear force, anything about the nuclei, anything is largely controlled by the strong force. The final one is the weak force. We very rarely see the weak force. Okay? The only times you see the weak force usually is where a nuclei decays into another one, radioactive decay. Okay? So if you've ever, we're not going to go through too much radioactive decay, but there's different types of decay, right? There's alpha decay, beta decay, and then gamma ray emission. And beta decay, I'll give you an example of beta decay in a second. That force is mediated by the weak force. Okay, so the weak force is a small force. Again, it's very, very small, and it mediates keeps certain things together in the nuclei. It's kind of rare, right? And typically, what you see effects of the weak force are not things being stuck together, but the presence of the weak force prevents things from falling apart. Okay, so it's kind of like a last ditch effort. All right, so it's kind of like it's not really something that keeps things together, pulls things together. It just keeps them from falling apart, which is why it's called the weak force. And the carriers for the weak force weren't observed until the late 70s, and they're called the W and Z boson particles. All right, there's 2 different ones, and they're called the W and the Z. All right, we won't worry about those. All right, let me give you an example of what the weak decay modulates. I'll just put it here on the board. So here's an example of beta decay of a nuclei. This is probably the most common form of beta decay, or at least what chemists like to think of a useful way to use beta decay. It's the decay of carbon-14. Right? We use that for radio dating things, like fossils and stuff. The decay of carbon-14 is set. The rate at which it's set is by the weak force. The weak force determines it. And the weak force mediates this decay, which causes carbon-14 to decay to nitrogen-14. It releases an electron and releases another particle. This is called a neutrino. Right, so that's the next particle we haven't seen yet, a neutrino. Neutrinos are typically particles that arise from weak mediated decays. Okay, there are the neutrino in some ways is the most abundant particle in the universe. There are trillions and trillions of neutrinos running through you at this very moment. Right? There are more neutrinos. There's a neutrino flux through your body is greater than the electron flux through your body. Billions and billions and trillions of neutrinos are coming through your body from the sun constantly. Because there's lots of weak decay, beta decay processes in the sun that generate a lot of neutrinos, and the sun's constantly sending out neutrinos. The reason why we didn't observe them until the 1990s is that they're really, really small, and they only interact with the weak force. Okay, so they don't interact through the electromagnetic force. Okay, so most things, like if you pass an electron through a material, the electromagnetic force will capture it or deflect it. But a neutrino will just pass through a material, electromagnetic material, like a metal, because it doesn't interact with it doesn't interact with the electromagnetic force. So most of the time, neutrinos just pass through you as if it's nothing, right? And there are really, really complicated, advanced ways to detect them. There are what are called neutrino observatories throughout the world, and these are very, very hermetically sealed environments. Typically, they're underground, deep underground, and they use a very, very, very high purity, heavy water, deuterated water to detect neutrinos. And they seal these containers, these environments, these observatories really, really well, because you want to make sure that there's no electrons or any other particles coming in there. Right? You want to filter out all the big stuff, so only the neutrinos can come in and you can detect them. Right? They're very, very hard to see. Right? So these are really small. Small and abundant. Okay, so the weak force is what mediates these decay processes. Okay? And it's a rare event, and it generates a unique particle that is very weak, right? Because it's a weak, if you can think about it, that because it's a weak interaction, the particles that come from it are also very weak and not very strongly interact. Okay, so those are our four forces. I'll talk a little bit about these carriers in just a second. Right, well, because these are particles, right? We can detect photons, right? Of course we can detect photons. There's a trillion of them in this room right now, right? And we can detect, we can't quite detect gluons, and I'll tell you why in a second. And we can also detect WBs and bosons. Right? So these are things that can be seen. A really famous place where they see these things is at the large, what's it called? The Large Heavy Ion Collider across the Sound in Brookhaven National Lab at Stony Brook on Long Island. They make these particles all the time. In fact, the place where they discovered the gluon, I think, was at the Ion Collider at Brookhaven. That's one of the original places where they did these gluon experiments. Okay, so let me keep going. So those are our forces. So let's talk about a little bit about the zoo of particles that we see in the universe. Okay, so let's just again very, very briefly go over the particles relevant for chemistry. All right, and our atoms only have three types of particles, right? Protons, neutrons, and electrons. Right, we call an electron E minus. Right? It has a charge of -1. It also has what's called a spin, which is 1/2. A spin of 1/2. Right? This is our color, if you will. What we'll find is that electrons can be +1/2 or -1/2. Think about when you do electron configuration in general chemistry. You have a spin up and a spin down electron in your orbital. Right? That's spin 1/2 and -1/2. The up and down electrons, right, or black and white color. So they can be 1/2 or -1/2. I guess I should put plus or minus here. There's two different flavors, if you will, two different colors. And as I told you before, the size, they're about right around 10 to the -30 kilograms, and no shape. All right, they're points, as far as we can tell. All right, people have looked. I think the sensitivity we have, the lower bound we have on the radius of the electron, is about 10 to the -30 meters. Okay? So that's a really, really, really small size. It's still a point even at that scale. All right, so the electron effectively is a point. All right, it's a massive point. Now, interestingly, we'll see in a second, there are particles that don't have what we call fractional spin, right? This is a fractional spin, 1/2. We'll see a lot of particles that have 1/2 spin. But there are particles that have integer spin as well. Spin of 1, spin of 0, spin of 2. Atoms often have these. And these are different types of particles. All right? So there are two different major classes of particles of spin. There are what are called fermions. These are particles with fractional spin. All right, 1/2, 3/2, 5/2. Right? Fermions that have Some examples of fermions are electrons, and as we'll see, protons and neutrons are also fermions. Most of the particles that we can feel and touch and we use on a regular basis, but the things that we think of are usually fermions. They have a half spin, and they have a very, very unique property. And I'll explain that in a second. So let me, just a sec, let me add another page here and scroll over a little bit. All right, so the other particles we have are protons. I have the mass of the proton here somewhere. Yeah. All right, so a proton has a charge of +1. It has a spin of plus or minus 1/2, just like the electron. Its mass, this is a different unit. I apologize. I'm going to use a couple different units here, but it's just slightly larger than an AMU, which 1 AMU is this is just slightly smaller than a hydrogen atom. A hydrogen atom is 1.01 AMU, something like that. So it's just, most of the hydrogen atom is a proton. The proton's most of the mass. All right, it's a big particle. It's about 100, I think it's 1,000, is it 100 times bigger? 1,000 times bigger than the electron. Electrons have 1,000th of the size. And it also has a radius. I don't actually know what the radius is, but it has a size. It's I think it's like around, actually I'll Google it really quickly. I don't actually know off the top of my head. So the interesting thing about the proton, unlike the electron, is that it actually has a physical size. What is the proton radius? I'm sorry, I don't remember it. Okay, so it's about so the radius is about 0.8 times 10 to the minus 15 meters. Very, very small. All right, so let me compare that to something. All right, so this is the radius of if you think about the proton as a sphere. Right? This is the radius of that sphere. The distance, the average distance between an electron and a proton in the hydrogen atom is 5 times 10 to the minus 11. Okay, so it's about 10,000 times, the size of the proton is about 10,000 times smaller than the average distance between the proton and the electron. All right, so let me just draw that for comparison for you, just to give you a sense of what that looks like. So here's my nucleus, here's my proton. Actually, let me do it like this. So here's my electron here, and it's at a distance of, let's say, about 0.5 angstroms. That's 10 to the minus 10 meters. 10 to the minus 10 meters. 0.5 times 10 to the minus 10. And there's my proton right there. So the proton radius on a scale of angstroms is about 0.11, so it's a factor of 4. 1, 2, 3, 4. Right. The radius of the proton is about that, right? So there's a ton. The take-home point is tons of empty space in an atom. Most of an atom is empty space. Right? The electromagnetic force between electron and proton likes to sit around an angstrom. Right? And the strong force likes to bring everything into 1,000th or 10,000th of an angstrom. Right? So we're talking about 6 orders of magnitude, 5 orders of magnitude in size difference. Right? So the nuclei, despite being very, very heavy, is tiny compared to the scale of the atom. All right, that's how strong the weak force is, right? It really brings in that mass really, really close together. It's really, really strongly bound in there. Everything's crunched together. All right, and we have other. Of course, we have one more particle in our nucleus, right? The neutron. It has a charge of 0. Bless you. It also has a spin of 1/2. It is slightly, if I remember correctly, it's about the same size as the proton. As we'll see, they're basically made out of the same stuff. And the radius is about the same. About the same. All right, so the proton and the neutron really aren't that much different in terms of size. The only difference is one's charged and one's not, and that makes a big difference. I mean, we'll see in a second. Protons and neutrons couldn't be any different from each other, despite the fact that they have very, very similar properties except for their charge. Now, the interesting thing is that you can take a proton and split it apart. All right, if you take a proton and you put it at really high energy, the proton falls apart and the neutron falls apart. It turns out that they have constituents inside them. The proton and neutron aren't fundamental particles. They're composite particles, which is why they have a size. Right? And there's a specific type. These composite particles have a name. They're called hadrons. The LHC, the big collider in Switzerland, is called the LHC, the Large Hadron Collider. Right? It was built. The LHC was built to collide protons together and blow them apart. That's why it's called the Large Hadron Collider. It takes protons, hadrons, and collides them together at very high energies. And when you collide protons at very high energies, they break apart into a million pieces. But what you find is that at the fundamental level, protons and neutrons are made out of a combination of 3 particles. Right? They have 3 particles inside of them that are all connected by gluons. And hadrons are made up of, so the hadron is made up of a set of particles called quarks. Right? The quarks are fundamental. They don't have a physical size, right? Just like the electron. The quarks are fundamental. They're not made up of anything else themselves. Right? So a proton and a neutron, you can kind of think of them as they're composite particles. They're almost like molecules, right? They're a connection. They're a set of smaller particles all connected with some springs, which are the gluons. They're connected by gluons. Right, so you can kind of think of as protons and neutrons kind of as very, very fundamental multi-particle systems that kind of can gel together. And when we look at them at low energy, right, when we do chemistry, we're at low energy chemistry, right, near room temperature, they just look like one particle. The proton looks like one particle, but as you increase the energy, you'll realize that they're actually soupy, and they're made up of these quarks. And protons and neutrons are both made up of 3 quarks, odd number of quarks. Have 3 quarks. And let's talk about the quarks. There are 6 of them. There are 6 quarks. So I'm going to draw a little box here, and we'll put the quarks inside of this box. Right, there are 6 of them, so I'll have like this. Right? The first quark is called the up quark. It has a U for up. Right? You have like a periodic table of quarks. There's the charm quark. Literally named charm because, I don't remember why it's called charm. I think it was because there was some bad joke that physicists made about it. There's the top quark, which is T. The down quark. The strange quark. And the bottom quark, which actually used to be called the beauty quark. But they changed it because they thought it was a little misogynistic. All right, so there are 6 universal particles that interact through the strong force. These interact through the strong force, so they're connected through quarks. And they have very, very interesting properties. Very interesting properties. They have a spin and a charge. So I'm going to write the spin in red and the charge in yellow. And not surprisingly, remember that the proton, the neutron are made up of 3 quarks. I'll explain which ones they are in a second. But they're all spin 1/2. The particles that they're made up of are also spin 1/2. So it's not surprising that all of the quarks are spin 1/2. They're all fermions. In fact, most particles in the universe are fermions. But the cool thing about quarks is that they have fractional charge. They don't have a unit charge. They have a fraction of the charge. So the up quark has a charge of 2/3. The charm quark has a charge of 2/3. The top quark has a charge of 2/3. The down quark has a charge of -1/3. Strange -1/3. And bottom -1/3. All right, so when you add quarks together, right, let's imagine, for instance, we add an up and a down. Let's say up and a charm together, for instance. The total charge will be 4/3. But then we add another particle, a down quark. So now the charge will be 4/3 -1/3, 3/3 plus 1, right? We'll make a proton, a positively charged particle, right? So this was real tell that protons and neutrons are made out of quarks, because when you add the quarks together, you get the charge of the composite particle. You just add them together. So let's look at that really quickly. So a proton is 2 up plus 1 down. Oops. Right? And so if we look at the charges for 2 up and 1 down, we have 2/3 plus 2/3, that's 4/3. And then we subtract a down, which is a -1/3, we get a charge of +1. Okay? So the charges all add together. Quarks provide a fractional part of the fundamental charge for the nuclei. And a neutron is 1 up and 2 down. Right? You get a +1/2, a +1/3, and sorry, you get a +2/3 from the up, and then -2/3 from the down. You have a net charge of 0. Okay? Now, the interesting thing about quarks, so the quarks themselves, they're connected by gluons, right? Gluons are really, really strong, right? So you have to have, in order to take a proton and pull it apart, right? Let's say I want to take this apart and I want to break these 2 ups and this 1 down apart, like this. It takes a lot of energy to do that, okay? Tons and tons of energy. In fact, it takes approximately, I would say, somewhere on the order of okay. So I'll just give you an example, because we're in. I have to do these units carefully, because we're at the point where energy and mass are the same. So a proton's mass, they report this. Physicists report it at a unit called mega electron volts. And I'll convert that to something more useful for you guys. An electron volt is about 97 kilojoules per mole. Okay? So a couple EV is about the strength of a bond. Okay? A bond is typically about 400 kilojoules per mole, so it's about 4 EV. Most chemistry is about 4 to 10 to 20 EV. Okay? So for instance, the ionization energy of electron, of the hydrogen atom, how much energy it takes to remove an electron from the hydrogen atom, I'll write that here. Right? Remove an electron from hydrogen, the energy required for this is 13.6 EV. Okay? So this kind of gives you a sense of where energy in chemistry is, right? It's about 10 EV, give or take. 10 to 40 EV. Let's say 1 to 40, 1 to 50. That's where you get to, once you get to be above 50 EV, you're starting to remove a bunch of electrons and molecules. Right? So a proton on the mass of the proton on the EV scale, remember E equals mc squared. So the proportional is 938 mega electron volts. And the binding energy of a proton, so the binding energy of a proton, I don't actually know the exact number, but it's close. Somewhere around 60 giga electron volts. Right, so you need to, right, so think about the difference between this is 60 times 10 to the 9 electron volts. Right, 60 times 10 to the 9 electron volts. Right, so it's about 1 billion times higher energy than you need to ionize an electron to pull apart a proton. Okay, that's a lot of energy. All right, these are the energies that they get at the LHC and stuff like that. The collision energy at the Large Hadron Collider, the amount of energy they create, is about a tera electron volt, a trillion electron volts. That's a lot of energy. Right, that's enough energy to blow everything apart. Right, and in order to see particles. Right, in order to see particles that release here, you've got to have energies this large to break apart a proton. Right? So you have to have really, really high energies to see these things. All right, well, what happens when you break apart a proton? Well, it doesn't break apart in the way that you think it does. You try to break apart that proton as many ways as you want. I don't know where I put my pen. Is there a pen over there? Oh, it's on the counter. Sorry. But what you find is that when you break them apart, you form pairs of quarks. All right, so if I took the 2 ups and the 1 down, the 2 ups, for instance, I have to think about the math. We have to do it right. There's some symmetry things. But the idea is that if you have 3 particles in here, you're going to break it apart. Let's say separate. You put the ups on one end and the down on the other end. A quark by itself can't exist. It has to always have another pair connected to it with a gluon. Quarks only come in pairs. So when you pull a proton apart and break it apart, some of the quarks will fly off in pairs, say like an up and a down together, but you have 1 up left over. The up will break into 2 smaller quarks. Sometimes there's what we call anti-quarks. There's anti-particles as well. I haven't talked about that. But they'll break apart, and they're always found in pairs. You can never find a quark by itself. All right, and the harder you pull on them, now this is the weird thing. This is unique to the strong force. So if you think about the electromagnetic force, if you have 2 magnets attracted to themselves, as you start to pull them apart, the force gets weaker, right? The further apart they are, the less magnetization you have, the less attractive they are. With quarks, it's the opposite. The harder you pull, the harder they pull against you. Right? So the strong force, that's why it's called a strong force, is that it has the opposite distance dependence as any other force does. Remember, gravity and the electromagnetic force go as 1 over r. So the further, or 1 over r squared. So you double the distance and the force goes down as a factor of 4. But the strong force is the opposite. You make them go further apart and the force increases. It pulls them together even harder. Right? So it's impossible to pull quarks apart. And if you pull them far enough apart that you kick off 2 of them, then the one that's remaining over will split into 2 smaller ones that will then combine together. Right? Quarks always come in pairs. Right? This was discovered in the 1970s, and it's a very unique property. Right? This is why nuclei are really, really stable and really, really strong. It's really hard to break them apart, because the harder you pull on them, the harder they want to come back. Right? They have the opposite effect of the other forces. The strong force is stronger at higher distances. Right? So that's very unique, and that's why that's one of the reasons why we exist in the first place, is that the energy scales of things that happen in the universe aren't anywhere close to the point where protons and neutrons are going to start breaking down, especially when they're together, because the forces are so strong, and the harder you pull on them, the harder they pull back against you. Right? And that's what gives us that strong stability. Any questions so far? Okay. So those are our big sets of particles. I wanted to say, to make just a couple of notes. So if you, just about a bit of a notes about what I called before fermions, and I think my thing's about to crash again. All right, let me just do this on the board. It's not to waste any time. This is just, I'm just not having much luck today with my stuff. Okay, so I wanted to talk very briefly about two different types of classes of particles, or atoms also count here too. Atoms can also fall into these. One of them I mentioned. So most particles are fermions. These have fractional spin. So they can be plus 1/2. Typically, most of them are plus or minus 1/2, like the electron. Right? There's another type of particle called a boson, which have integer spin. Right? So they can be something like 0, 1, 2, blah, 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 so on and so forth. Right? And bosons and fermions have very, very unique properties. They, in fact, almost act as if they were different. Well, they are very different, but they have very different properties. Fermions have a very unique property. Fermions have what's called the Pauli exclusion principle. Which means that only one fermion of a given spin can exist in a single space. Okay? What does this mean? Well, let's think about electron configurations for atoms. Right? So let's look at helium. Right? Helium has a 1s shell, right? And how do we, right? Helium has 2 electrons, so how do we fill it? What? We put one here, and we put one here, like that, right? That's how we do it in general chemistry, and there's nothing wrong with that. That's totally fine, right? You have an electron, right? What does the up arrow mean? It means it has spin of plus 1/2, and the other one has spin of minus 1/2, okay? And those are the only 2 electrons you can put in a 1s shell, all right? So what if I did this instead? What if I put them in the 1s shell together with the same spin? Right? This is not allowed. Right? Fermions require that if you're think of the 1s orbital as a spot that you can put an electron. We'll talk more about what the 1s orbital is. But it's a spot that can fit an electron. Right? And it can fit 2 electrons, but because electrons are fermions, you can't have 2 electrons of the same state or the same type in one spot. So when we fill electron shells, electron orbitals, right, each orbital takes 2 electrons, and the reason why it takes 2 and exactly 2 electrons is because there's only 2 different ways to put an electron into it, right? Spin up and spin down. Okay, so this doesn't work. Right, you can't do that. Right, it's not allowed. No fermion can exist in the same state in the same space as another one. All right, so they can't stand on top of each other. Right? That's what enforces the electron configurations that we have for atoms. You can only have 2 electrons per orbital. Because if there were any more, there's only 2 possible ways to have an electron, right? +1/2 and -1. There's up and down, right? There's black and white, as we saw. And so we can only have 1 black and 1 white, or 1 up and 1 down. That's it, and 1 state. So then we have to have more orbitals to put more electrons in, right? The 2s and the 2p's and the 2d, the 3s's, and so on. Right? And most particles are like that. Electrons, protons, right? You can only fit, works exactly the same way as electrons do. They all have the same property, this fermionic property, that they have this exclusion principle. Bosons, however, in bosons, as many identical particles as you like can exist in the same space. Okay, so imagine if electrons were fermions. All right, so let's look at carbon, for instance. Right, so let me write the carbon now. 1s, 2s, and then the 2p's. Right, the electron configuration for carbon. You're missing one. No, that's it, like that. Right, so this is assuming that these are electrons or fermions. Right, this is real life. Right, and this satisfies the exclusion principle, right? We can only have one type of electron per state. So we have an up and a down on 1s, up and a down on the 2s. And then we fill the 2p's, they're not completely full yet. All right. What would it look like? What would carbon look like if the electron was a boson? What would be the ground state electron configuration if the electron was a boson? Well, I can still draw the same set of orbitals, but bosons can all exist in the same space at the same time. So what would I have? All the electrons would be in the ground in the core, right? Because they can all exist in the same space. Right, so it's probably a good thing that electrons aren't bosons, because then we wouldn't have atoms at all, right? There would be no chemistry at all. Every atom would basically be exactly the same, just heavier, because all of the electrons are all buried in the lowest valence shell. They're all going to sit really close to the proton and the neutron as close as possible in the lowest energy state. There's no difference between carbon, helium, chemical difference between carbon, helium, mercury, and zinc, right? They're all in the same state. You just have more electrons in carbon than you would for helium. Right? There'd be no chemistry. Right? So chemistry is dependent on the fact that electrons are fermions, because that gives us diversity. Right? It means a lot, right? If you can only fit 2 electrons per orbital, well then the difference between carbon and neon, right? Neon, I fill these up, right? That's a very, very different world than the carbon atom, right? The carbon atom has 2 unpaired electrons in the 2p, and the neon has no unpaired electrons. We know they have very, very different chemical reactivity, right? A neon is just a noble gas; it doesn't react at all, because all the electrons are paired up. Carbon, of course, reacts with everything. Right? It forms bonds with just about anything. It's one of the most promiscuous atoms in the world, in the universe. So it's important, essential, that fermions can't exist in the same space, because otherwise everything would be in the ground state. Right? There wouldn't be any chemical diversity. There would be no chemical reactions. Everything would just be buried. You wouldn't be able to pull those electrons out, and there would be no chemistry. Okay, but there are many different types of particles that are bosons. There are different types of atoms, for instance, that are bosons. We'll talk about that later. Okay? So there are composite particles, say atoms, which are composite particles of protons, neutrons, and electrons. They can be bosons overall. There are certain types of atoms that can all exist in the same space. A good example of that is helium-4. The most common form of helium is a boson. And if you cool helium enough, it forms what's called a superfluid. And a superfluid is a material where effectively all of the atoms exist in the same state, in the same arrangement, in the same, if you think about the same orbital. Okay, you have all these atoms and they all cool down to the ground state, they're all in the same state. You have N atoms, it might be 10 to the 40, right, whatever the size of your liquid is. They're all in the same state, as if they've all gone down into this ground state here. Okay? There's another type called a Bose-Einstein condensate, which you can make from alkali atoms, the most common way to do it, where again, you're putting many, many, many atoms into a single state. All of the atoms are represented by the same state. They're all in the same space, and they all act together as if they were one object. Right? And only bosons can do that. These physics are super important. As I said, this is the reason why chemistry exists, is because the fact that electrons are fermions. And it has very, very wide-ranging implications. Okay. So, I lost my notes, unfortunately. I'm going to have to figure that out. So, our electron is a fermion. Which means no two same electrons can exist in the same state or space. They repel each other. Okay. There's one other particle I want to mention. And this one is entirely irrelevant to us, but I think it's important because it's the most recent particle that's been discovered. And it's the reason why they built the LHC, and for instance, and that is a boson itself, the Higgs boson, or what the press called the God particle about 10 years ago, which is a terrible name for it. The Higgs boson is a very, very unique particle, and there's a reason why people were so interested in it, because the Higgs boson, I'm going to get rid of bosons, there's only one of them. Typically, it's called H0, the Higgs boson. The Higgs boson is a very, very interesting particle. And it's hard to explain how interesting it is without giving you a little context. So it turns out, this is something that was discovered in the 1960s, and it's won many Nobel Prizes, is that when you get to high enough energy, so about 100 giga-electron volts, really, really high energies, at high energies, the electromagnetic force and weak forces merge, become one. They unify. All right, so once you get up to high enough energy, particles that interact with the weak force but don't interact with the electromagnetic force and vice versa, they start all interacting with each other. All right, the electric force, the photon, the force carried by the photon, the electromagnetic force, and the weak force, they all become components of the same force. It's called electroweak unification. And at this force, so there has to be some particle. So what it turns out is that, so you have at high energy a single force, and then as you get to lower and lower energies, that one force magically splits into two forces. Okay? So there's a critical energy at which the electroweak force becomes the electromagnetic force and the weak force apart, right? So that's the splitting. Interestingly, for those who took my class last semester, when we talked about critical points, where we go from a gas-liquid coexistence to a supercritical fluid, right? We go from two components to one component. That phase transition is precisely the same physics as the electromagnetic force and the weak force splitting into two forces. Exactly the same physics. They're both phase transitions, second-order phase transitions, the exact same chemistry, not chemistry, but same physics. Very, very similar. And so at high energy, you have these phase transitions as well, and the most important one is where the electromagnetic particles and the weak particles all become one phase instead of two separate phases. All right, there has to be something that mediates that breaking apart. Right? There has to be something that mediates the weak particles, that mediates the splitting, if you will. There has to be something that causes that, a mechanism that causes the electroweak force to split at low energy to the electromagnetic and the weak forces. And that's the Higgs boson. The Higgs boson is the particle that mediates this. It mediates the electroweak splitting. And the energy or the mass of this particle is on the size of the interaction. So the size of the energy scale where it breaks apart. So when you're at energies lower than the energy of the Higgs boson, you have two forces. And when you're at energies above the Higgs boson, roughly, I think it's Higgs boson divided by 2. I think there's a factor of 2 in there. But once you're on that scale, if you're lower than that scale, you have two forces. And when you're above that scale, you have one force. And so we saw that the electroweak. So in the 70s, we discovered that the electroweak unification occurred. This was proven theoretically and experimentally, but we could never find the Higgs boson, right? This is the thing that ultimately determines all of these effects. It's kind of like the glue that holds the whole theory together, that this particle is ultimately what mediates the whole thing. Right? There's this master particle that is effectively the force carrier for all of these interactions, all right, that creates this. And that's the Higgs boson, right? Which is why we spent billions and billions of dollars to go look for it in the 2000s with the Large Hadron Collider, because it's important. It's the last remaining part of the theory we didn't understand. We see these behaviors, this phase transition between electroweak and unified and ununified. And the thing that causes that, we don't know what it looks like. So we went go looking for it. And the Higgs boson was discovered in 2012. Interestingly, it has spin of 0. It's a boson. In fact, it's about the only naturally occurring fundamental boson. I think there's a couple others, but for most particles in the universe are fermions. The Higgs boson is spin 0. It's very unique. And it has a mass of almost exactly 125 giga-electron volts. Right? That is about an AMU. If I want to convert that to AMU, it's about... let me think about it. So a proton's about 1 giga-electron volt. It's about 125 AMU. Maybe 130. Right? It's a big particle. Now you might wonder, well, why, if it's so big, right, that's like a large atom. Why can't we see it? Well, remember that mass and energy are the same at relativistic speed. So in order to see a particle that big, we have to be at that energy scale, right? Which is, this is insanely high energy. Right? You can only see this at very short time scales and at very high energies, right? Which is why we need a collider. So the Higgs is ultimately this fundamental particle. It spin 0. It has a mass. But what it does is as I said, is it provides unification for the EM and the weak fields, right? It mediates that interaction between electromagnetic and weak particles at high energy. And it also generates an effective mass for all particles. So it turns out there's another part of the Higgs mechanism. So not only does it mediate the electroweak force, but if the Higgs particle wasn't there, none of the particles in the world would have mass. All right, so the Higgs boson is what gives matter its mass. All right, this force between the Higgs boson mediates between the electric force and the weak force is what gives the electron its mass, and what gives the W and Z bosons its mass, right? Which then gives atoms mass. All right, so the Higgs boson, if the Higgs boson didn't exist, if the theory wasn't there, every particle in the world, in the universe, would be massless. The photon would be of course, the photon is massless. The electron would be massless. The proton would be massless. The quarks would be massless. Everything would be massless without the Higgs particle, right? So the Higgs boson is literally the connective glue that brings mass into physical reality, all right? The way it does that is extremely complicated, and I don't understand it, and I'm not going to sit here and explain it to you. It's not important. But the important thing is that there's this fundamental particle, and this is why it was so important, because this particle is the glue that holds the entire model together. Right? If it wasn't for the Higgs boson, none of the smaller particles would exist at the masses that they do, at the energies they do. They wouldn't have the interactions they have, right? The Higgs is the master particle, if you will. That's why they called it the God particle, because in some ways it is the omnipotent particle of the standard model. It determines everything about matter. But the important thing is that that's only up to a certain limit. We don't actually know. There might be something more fundamental than the Higgs particle, but this is as fundamental as we get. Okay, so the take-home point that I want to give here for today is that chemistry is that a lot of what I've just told you is entirely irrelevant for us because chemistry is low energy. Right? What did I say? I said that the energy scale of chemistry can be defined by the ionization energy of hydrogen. Right? I would say that's the first fundamental particle, or the first fundamental chemical reaction, the removal of an electron from a hydrogen atom. Right? And the energy for this is plus 13.6 roughly EV, electron volts. Right? That's about 1,300 kilojoules per mole, 1,200 kilojoules per mole, give or take. Right? Of course, chemistry is a little lower than that, right? The delta E of forming H2, for instance, is about, I have to double check, but I think it's about minus 4 EV, right? The bond strength of hydrogen, right? So this is where chemistry happens. Right? These are the two most fundamental processes in chemistry, the removal of an electron from hydrogen and two hydrogens forming H2. And these happen on the scale of about 10 eV. Right? So when I talk about things that happen at 100 gigaelectron volts, right? 100 billion electron volts, right? Or the binding energy of a proton is about 80 gigaelectron volts, right? These are millions of times higher energy than chemistry. Right? So in chemistry, a lot of these effects, these high energy particles and stuff, we don't have to worry about them because we don't ever see them. We only look at things at very, very low energy. Right? And chemistry happens at about an EV. Right? That's why we choose that unit. An EV is an appropriate unit for chemistry. Right? Everything kind of falls around 1 to 10 EV. Right? So chemistry is low energy. What does that also mean? Well, that means also that because it's at low energy, 1 EV, that also means we're at long length scales. Right? We don't have to worry about microscopic particles because chemistry happens at at the length scale of the electromagnetic interaction, which is about 0.5 angstroms. Right? About an angstrom. All right? So we don't have to worry about things that are 10 to the minus 15, 10 to the minus 20 meters, or tiny, tiny particles, because interactions on the scale of 1 eV tend to happen around an angstrom. And not surprisingly, this also means long time scales. We'll see an interesting relationship in a couple of days, a couple of weeks, which says that the uncertainty in energy for a quantum mechanical particle is on the order of 1 over the time it exists. Right? This is called the energy-time uncertainty relationship. Okay, so if you have a particle that exists for a very, very short amount of time, it also has some uncertainty in energy and vice versa. So if you, for instance, create a particle that has a large amount of energy, it can only exist for a short amount of time. Okay, so the time and energy and physics are inversely related to each other. So not surprisingly, if we're at low energy scales, 1 eV, we're going to be at long time scales. Right? And the time scale that chemistry typically happens at, we'll learn more specifically, there are different time scales in chemistry. But let's just say on the order of about, what do I like? 100 femtosecond, let's do a picosecond. 1 picosecond, which seems short, that's 10 to the minus 12 seconds. Right? But that tends to be about where chemistry happens. And there are plenty of techniques where we can get this time resolution. Right? So if we want to monitor chemistry on its fundamental time step, right? We're going to watch a reaction occur in real time, for instance, on a molecule by molecule basis. We got to monitor time steps on this time scale, and we can do that with lasers now. Now the question you might ask is that if chemistry happens on this time scale, 10 to the minus 12, 10 to the minus 10 seconds, what's the time scale of the Higgs boson? Well, the Higgs boson is 1 billion times bigger. The energy scale of the Higgs boson is 100 billion times bigger than the energy scale of a bond. So the time scale of the Higgs boson is 100 billion times smaller than this. Right? So that's about 10 to the minus 21, 10 to the minus 22 seconds. Right? The Higgs boson lasts for a tiny, tiny little bit of time. Infinitesimally small compared to the chemistry. Right? Which is why we don't care about that stuff. We care about electrons. We care about bonds. And the thing that I want you to take home in this last 30 seconds and this is just a one-sentence thing as I start to fail. All right, I'm just going to write it on the board. I am not having much luck with my screen today. In fact, I'm just going to put the screen up. The point I want to make to you today, the whole point of this, is that chemistry is an electromagnetic theory. Right? Chemistry occurs at the scale of electromagnetism. Right? We said that the average distance between a proton and an electron is about 1 angstrom. And the bond length of hydrogen is about 1 angstrom. Right? Everything happens on this length scale. Right? And this length scale is fundamental to the electron and the proton, right? And to the electromagnetic interaction. Right? So chemistry is purely an electromagnetic theory. Everything about chemistry is defined by electromagnetism. All right, of course, the nuclei are bound by the strong and the weak forces, and this can play a role in nuclear chemistry, of course. But actual chemistry is just electrons and protons moving around. So we only have to worry about the electromagnetic theory. All right, and not surprisingly, because we're doing things with electromagnetic theory, right? Protons and electrons and neutrons, our force carrier is light. The thing that transfers energy from electron to a proton and vice versa is light. So not surprisingly, light is the way that we're going to want to manipulate light chemistry, right? We're going to want to use light to talk about chemistry because the entire system is defined by electromagnetism. So if we want to manipulate an electromagnetic system, we should use the particle that's literally created to manipulate that system, and that's the photon. Light's a light particle, right? So chemistry and light are intricately connected because of these physics. And that's why spectroscopy is so important, right? That's one of the reasons. We'll talk about other ways that we can use light for chemistry as well next class. But I want to leave it there, right? That the interaction between light, electrons, and protons, and neutrons, electromagnetic materials, are ultimately what defines chemistry, and that's what we want to explore. Okay. All right, we'll come back to this next class, guys. Sorry about the problems. My recording's not going to be great. But I'll post the notes.